I'm Law Chai Hong. Today I'm going to talk about the problem 3B report. Previously in 3A, you already know that there is two loops. So loop 1 is to control the methanol compositions in distillate flow by manipulating reflux flow. So the process gain is equal to the distillate compositions over the reflux flow, and the disturbance gain is equal to the distillate composition over the feed rate. For loop 2 is to control the methanol composition in bottom column by manipulating reboiler flow. So the process gain here is equal to the bottom compositions over the boiler flow rate, and the disturbance gain is equal to the bottom composition over the feed rate. Now I'm going to explain about how to calculate the GD and GP, but I will use only one example to show the calculation. That is, I'm using the GD in the top column. So this graph is the 5% step change graph. We show that this graph is stepping up, and this graph is the open loop response graph. And we are going to use method 2 to get the parameters. First, the parameter that we have to determine is this triangle, which is the difference between starting point and the stable point. And the sigma here is the feed rate to achieve stable, which is this 2 point. And the method 2 is about using the 63% and 28% method. And you need to determine this by getting this line. This line is equal to 0.978 plus 0.63 triangle. And this then you draw the vertical line, then you will get the T63%. And this T38% you can get by equal to 0.978 plus 0.28 triangle. However, this T63 and T38 need to minus this line, because this is where it starts to become stable. So this line is 15. So here you need to minus 15, so equal to 70 and 27. And the KD is equal to triangle over sigma, then you get 0.007930, and the tau is equal to 1.5 bracket T63% minus T38%, and the time here is equal to the T63% minus tau. For this graph, this is the step down graph. So this is the negative 5% step change graph. And basically, how it determines the parameter is same as the plus 5% step change. So here, you will get the KD, the tau, and the time. So we will be taking the average of these two graphs, which is the plus 5% and the minus 5% value, divide by 2. You get the 0.8921. And then the tau is equal to 64.5, and the time is equal to 5.5. So why we want to determine the first order plus time delay equation? This is very important to use for the Cohen-Coon technique. So this is the formula for the MOPTB. Then you just substitute the value inside. Okay, so all this step is same for the GP in the top column. So the GP in top column, you'll get this. For bottom column, we are getting this GD and GP. That's all. Thank you.
I'm Fatin, and I will explain about rough stability. For top column, we start with parameter GP, GV, GM, GC. So GP we get from the calculation. For GV and GM, we assume the valve dynamic to be negligible. Reflux rate change is from 0 to 15, and signal given is in the range of 1 to 100%. Then GC equal to KC. Since it is P controller, we move to characteristic equation. Characteristic equation of system is 1 plus GP, GV, GM, GC equal to 0. So we just substitute this GP, GV, GM, GC, and we get this form. Then using 1 over 1 paid approximation, we calculate exponent negative 5.5s. So theta here is 5.5, and we get this. We just substitute back, rearrange, and get quadratic equation form. We proceed to rough array. We can see all the coefficient here is positive, so we arrange according to power of s. Based on this equation, we calculate B1. From this, when B1 equal to 0, we get minimum Kc, and same goes to this. We will get maximum Kc, so we can conclude that system will be stable if Kc is between negative 302.48 to 7396.61. Same goes to bottom column. We get GP from calculation. Then we assume final control element dynamic to be negligible. Range for QR is from 0 to 300,000, and signal given is in the range of 1 to 100%. Then from characteristic equation, we substitute GP, GV, GM, GC, and also this paid approximation calculation, and get this equation. For rough array, we use same method with top column. Then we get range Kc from negative 54.82 to 384.89.
Hello everyone, my name is Jasmita and I'm going to present about Cohen-Coon tuning. As we all know, there is top column and bottom column. We have to do tuning for both the columns. We have to find GPRC first, which is a product of final valve final control element transfer function and process transfer function and sensor transfer function. And for Cohen-Coon, to find the KC, the formula is different for every controller. As for PC, we can find KC by using this formula shown here. And KP, tau, and KP is stability criterion, and tau and theta we have already found in part 1, which my friends have explained. We just substitute in the values to get the value of Kc. And as for the Simulink part, we have to create this, we have to do this modeling in Matlab. We have to construct this transfer function, and it will generate a graph of this sort. And we have to do this for each controller for PI and PID, and compare the graphs to make a judgment on the stability. As for PI, we have to find the Kc and Ti, which is time integrated time interval, using this formula. Substitute in the values and get the Kc and Ti. And as showed earlier, we have to create a Simulink function and generate a graph. In the end, we have to do the same thing for the bottom column as well. And analyzing the graph, we have come to a conclusion that we are choosing PI controller. This is due to better stability by analyzing the graph generated in Matlab. That's all from me. Thank you.
Good morning, Doctor. I'm Wewan. Now I'm going to present the tuning method by using the online Ziegler-Nichols method. So by using this method, we need to draw up the block diagram. So as you can see, this is the block diagram for the top process, and where this is the transfer function for the WAF, transfer function for the process, and then the time delay for the process, transfer function for the disturbance, and also the time delay for the disturbance, and then this is the transfer function for the GM. So by using this method, first of all, we need to determine the value of KCU, which is the ultimate gain, by using the try and error of the PID controller. This one, by using a try and error of the proportional. So when it's run, it will show until it shows the constant graph like this one, and then this 2 peak, the distance between 2 peak is taken as the PU, which is the ultimate period, and the value of proportional P is taken as the KCU. So after having the number of KU and also the PU, we can calculate the value of KC, tau 1 and tau D by using the Ziegler-Nichols formula as shown in here. And then this the result for the KC for P, KC or PI, and also KC or PID is shown in here. After that, we transfer the value that we get and to put in here, where the proportional P is the KC value, integral I is the value of tau 1, and the derivative D is the value of tau D. After that, we can run the process. So you can see this the graph of show that the process of the PID. So basically this is the process, the step is repeated with the P controller and also the PI controller. While for the bottom process, right, is repeat the same things. First, we need to determine the KCU by using a try and error, and then determine the value of PU, and then calculate the value of KC, tau 1, tau D by using a formula, and then fill in the PIC controller and determine the graph.